I have talked about how using different materials to measure the same temperature, we might end up with a different answer. For example, even when we use a glass thermometer, say the alcohol might move more quickly at the low temperature than mercury, right? So they might actually give mercury and alcohol thermometer might actually give slightly different answer, and it might even be more different when we use other the changes in other materials like resistance or voltages and so on. So I asked the question whether it is possible to have a thermometer that does not depend on any of these material properties. Now, and the answer is yes, by using an ideal gas. So let me explain. Now you might ask, if I use an ideal gas, doesn't it depend on the property of the ideal gas? Okay, that is a good question, and the answer is this. An ideal gas is not a real material. An ideal gas is an imaginary material. So in that sense, it's not real, and therefore it doesn't depend on the properties of any real material. Now the obvious next question is, if the ideal gas is imaginary, how in the world can we use it to measure anything? Well, let's find out. Suppose I have a box of gas. Let's say I'll just say, for example, it is oxygen, and there are lots of these gas molecules inside moving around. And we know about the ideal gas law. It is PV is equal to nRT. So suppose that I want to use this gas to measure temperature. Now you have seen that we can use the expansion of a liquid like mercury or alcohol in a glass thermometer to measure temperature. So I can use, say, there are different ways I can use this. I can use the volume as well. If I can measure if I go and measure the volume as the gas expands at different temperatures, I can use that like I use the mercury thermometer. It's a bit more troublesome to set it up and measure, but it's possible. Now, for what I'm going to do is that I'm going to say that I would use pressure. Okay, I would use pressure to measure temperature. So I'm going to keep the volume fixed. Let's say I keep the volume fixed. Now let's see how I can use pressure to measure temperature. I can imagine like what I did with the mercury thermometer. All right, measure the pressure at ice point and steam point, and then use the degrees Celsius formula. Now, but for using the gas, when using a gas thermometer, this is actually used in physics for measurements, and although we don't see this in everyday life, it's big and troublesome to use. We would just use the glass thermometer, which is more and convenient. So if we want to set this up to measure temperature, we would not normally use the degrees Celsius scale. We would normally use the Kelvin scale because the T in the ideal gas law is in units of Kelvin. So that's definitely more convenient. But there is, so let me just quickly say how this Kelvin scale is calculated if I have a pressure. Remember that we had a formula for the degrees Celsius in terms of, say, the length or resistance of the material. So we also need a formula. And like in the case of the glass thermometer, we need fixed points. Right? In the glass thermometer, we had ice point and steam point. Here we need, let's see what we need. Let me write this down. Our fixed points in this case, that means the point where we refer our temperatures to, there are 2 points. One is the absolute zero, right, which is 0 Kelvin, of course, and the other is defined as the triple point of water. Triple point of water. Now, this is a tricky concept to understand. It's the point where where ice, water, and water vapor can exist together. Now, if you think about the ice point of water at normal atmospheric pressure, ice point is where we have ice. Let's say I have a box here, and that's water, and that's water vapor. Let's say this is a closed box. Now, at normal atmospheric pressure, ice point is 0 degrees. Ice point is 0 degrees. Is where ice and water can exist together. That's at 0 degrees, right? But the triple point of water refers to the point where we can have water vapor, water, and ice existing together, but with nothing else, with no air. So it's not possible to have atmospheric pressure. There is actually a very low vapor pressure, which is all there is. Okay, so with just water vapor, water and ice without any air pressure, that there is a temperature at which this will happen, and there's only one temperature. Okay, it's not a familiar situation, but I shall not go into the details except to say that in order for this to happen without you must not have any air pressure, so therefore no air. This must be in a closed container, and it will only happen at one specific temperature, and that temperature is 0.01 degrees Celsius. Okay, 0.01 degrees Celsius, and this temperature in degrees Celsius, that's the value. Now in Kelvin, it is defined to be 273.16 Kelvin. Okay, so that's the triple point of water. So at this temperature, the Kelvin temperature is taken to be exactly this value. So it looks very strange, but if you think of it, it's really not any more strange than taking 100 degrees Celsius to be the steam point, except that, okay, number 100 looks simpler than 273.16. So if you like, this is just something that happened in the history of science. Okay, now let's come back to this. Suppose that I keep the volume fixed, and suppose that I can measure the pressure. Okay, so measure pressure. Now I shan't talk about how we actually can measure pressure. Assume that we might have some gadget, some clever device attached to the box or in the box that can measure the pressure and tell us the value. Okay. Just going to assume that we can measure the pressure, and suppose that we measure the pressure at 0 Kelvin. Now we can never go to 0 Kelvin actually. So okay, let me start again. Forget the last sentence. Now suppose that I can measure the pressure at the triple point of water. Let me write down the formula here. So now the volume is fixed, so the volume doesn't change. N, same gas, same number of moles. Gas constant, always the same. Now the triple point of water is this temperature. Now I'm going to just to make it easier to write, I'm going to call this T with the subscript TR for triple point. So the triple point temperature is here. Okay. And now suppose that the pressure of this gas at that pressure is measured and has a certain value. Now I'm just going to call that P with the subscript TR. Okay, so if I now change this to a different temperature, I might cool it down to say liquid nitrogen temperature or heat it to 1000 degrees Celsius. So anyway, at that new temperature, suppose that I have a certain pressure that I measure. In order to find the temperature at that point, I suppose there's an unknown temperature, but I can measure the pressure. I can divide these two equations. Let's see what I get. If I divide these two equations, on the one side I get T over T triple, and on the other side I get P over P triple. Now before it gets too confusing, let me just repeat this. The pressures are what we can measure at an unknown temperature and at the triple point of water, right? Assuming that we can change the temperature until it is the same as triple point. So pressures can be measured with some pressure gauge. Temperature is what we need to find. Now triple point temperature is defined. So it's not measured. It's just defined to be 273.16. If you like, it's just made up by the scientists to be this value for historical reason. It is defined in much the same way as ice point is defined to be 0 degrees Celsius. So there's no reason why ice point should be called 0 degrees Celsius, except that it was decided for convenience many years ago. So this is just defined, right? This is what we have to calculate, and those two are measured, right? So let me just write those down. Maybe these two are measured. These two we need to find. We want to find, and that one is defined. Meaning it's decided, it's made up, or however you look at it, and then we just stick to this value, 273.16, which is this. Okay, now if you look at this equation, assuming that we have measured the two pressures, and we know this is 273.16, therefore we can calculate T. So therefore we have a formula to find the temperature. The temperature is P, the pressure at that unknown temperature, divided by the pressure at the triple point times T triple. I just move that to the other side, which is 273.16. And the answer is in Kelvin. So that's our formula, right? This is a formula that corresponds to the degrees Celsius formula we had in the last session for the length of the mercury or of the liquid in glass thermometers. So in Kelvin, this is the formula that we're looking at when we want to measure it in terms of some material properties. Now, so I have not actually answered the question yet about how we can actually know whether it is possible to have a thermometer that does not depend on material properties. So I shall have to do that in the next video.